We're in chapter 9. We started this new guy where we're going to basically go through the same thing with means. Again, as promised you, it was going to get ugly. I don't know how ugly it's got, but it's going to get uglier. We're going to start off by doing an example of a single mean sample. So I'll make up a little story and we'll create a confidence interval for it. And then we'll try and see if there's any significant information in that. So in this one, what shall we do? So let's suppose we collected data on professional basketball players, and the data that we collected was their height. And it ended up, honestly, I don't know. Give me a number. How many inches do you think an average professional basketball player is? How tall do you think they are?
6'5".
6'5", so 77 inches, right? So we'll pretend that we collected a sample of 100 professional basketball players, and the average of the sample was 77, right? So, and we're after the average height of every basketball player, professional basketball player at least. Now, that population is small enough that we could probably have done a census. Would you agree there's not that many professional basketball players? Unless you describe, minor league as well. But we're pretending for the sake of this story. And we got a standard deviation. And I'm saying it's 5 inches because I need a number. But you can imagine what that would be like, right? You just got a list of 100 guys. I'm pretty sure there's a place somewhere where you can find the height of all these basketball players, isn't there? You could probably go onto the team list and find it or something. So we'll assume that this data is good. And we're going to use it to find a 90, 95, or 99 percentage confidence interval. And I feel like I want to do a 90%. So basically, our questions are going to be finding confidence intervals and then interpreting them. Right, there's a guy here called degrees of freedom, which is 99. That's going to give me the magic t-score, isn't it? Because we use t-scores. And I'm going to zoom over here, and I'm going to make a little bit of a judgment call here, if I can find the darn thing. And there are two schools of thought to which guy you use. Well, it's a little bit awkward, but you see how the 90% is the second column. I hope it's not. Say, it wouldn't have been that hard for them to put this row at the bottom as well. But anyway, 99 is one of those two numbers. By sheer bad luck, it's the same two numbers, so it doesn't matter. But there's two schools of thought. If your table doesn't have it, wouldn't you say 100 would be a good choice, or 90 would be a good choice, right? You could round up or you could round down, or you could round to the nearest. And there's, as I said, there's two schools of thought. I would normally just round to the nearest one. It's probably going to make zero difference. And the t-distribution is itself fraught with some errors. So you're not really going to make a big difference if you're a little bit out. So based on this one, would you agree that 1.66 is the magic t-score? Okay, so I've got this online now. So whenever you've got questions, you just go there and look for the darn thing. So let's put the package together. Well, not quite. I need to find the standard error, don't I? And it's basically just that guy, right? So in this case, it's 25 over 100. Oh, how nice is that? It's 0.5. Came out really nice. So here we go. Our 95% confidence interval is the mean of the sample plus or minus the magic t-score for a 90% confidence interval times the standard error of the mean. And we had 77, give or take 0.5. Sorry, 0.5 goes there. And 1.66, 1.66 goes there. So it's 77, give or take 0.83. So it's somewhere in the region 76.17 to 77.83. So if this data was really good data, and we're pretending it is, then we could be 90% sure that the average height of every single one of the basketball players, right? So if you got them all and averaged it out, that the average would be somewhere in the region of 76 to 78. It's pretty good, right? So let's talk about conditions. You know, when can I actually even do this process? I haven't talked about that. When we did the proportion ones, can you remember that they had the NP, NQ bigger than or equal to 10 rule, right? That was essentially all you needed to worry about. A little bit harder when you do these ones. Here are the conditions. The population should be normal in shape. So it should look like that. Now, it doesn't need to be a perfect normal. There is a fair amount of wiggle allowed. So it could be slightly skewed to the right and it won't cause much damage. It could be slightly skewed to the left and it won't cause much damage. So roughly or approximately would maybe be a better phrase, normal in shape. It's not good if the data, right, if the population looked like that. Now you might think, oh, populations can't look like that. Do you know if you take the height of people and you do their heights, do you know you very often get that? Or weights. And very often the male-female split causes 2 bumps, right? Men, I think men are typically heavier than women. Pretty sure that's true, right? They're thicker bones, probably thicker heads, right? So if you did a distribution of a population where it was mixed with men and women, it wouldn't be as noticeable as that, but there would be a distinct, you know, unnormal shape thing going on because of that. So that's a biggie. And then size. Well, remember with the NP bigger than or equal to 10, it basically was there at least 10 people who said yes, right? And the other one is called NQ, and it also has to be bigger than 10. And that is, there should be at least 10 people says no. That isn't such a nice rule, but there is a rule. At least have 30 people in your sample if you want to be safe. Now, could you use it with 10 people? Could you use it with a sample of 5? Theoretically, yes, you could do that. But if you did, you also have to be aware that you can be less and less sure that the 90% confidence interval is actually 90%. As the sample size gets smaller, that 90% becomes very wiggly. Maybe you're lucky and it is, but if the distribution is really weird. So normal in shape and at least big enough to cope with it. I think I'll do just one last more single one and then we'll move on to the doubles. Okay, let's suppose we took as our sample, what are we doing this time? sample size of 32. And we found the height of 32 OC college students, and it ended up being 7 inches, which is what, 5'10". And we would like to use this to estimate the average height of an OC student. Now, the sample size is 32, so doesn't not just sneak by the 30 or more hurdle, right? So the sample size is big enough for us to be reasonably comfortable that we can actually do this analysis. I'm going to make the assumption that height is typically normally distributed. Would you agree that people are small, people are average, people are tall, but it tends to be reasonably smooth? So I think that is an assumption, but I'm assuming it's true. So it means I can do everything. The degrees of freedom in this particular question is 31. Oh, and the standard deviation happens to be 6 inches. The standard error is the square root of S over N. It's the square root of 6 over 70. We'll check that out. See what we get here. Square root 6 divided by 70, and I get the answer 0.293. Now I need a magic t-score. What confidence interval do you want me to do this time? Pick a number.
90.
I'm slightly confused.
Oh, well, let's start with David's confusion. What if I?
Why did we square the 5 and the basketball heights and we're not squaring the 6? And
Because I can't count, and I made an oopsie.
okay.
But well caught. I'm too busy worrying about this darn table that I didn't focus on the job at hand. So the new value is 0.717. Right. So now you're not confused because I fixed the mistake I made. What kind of interval do you want? 90, 95, 99?
Let's
90.
do 9.
Well, I got 2 people on 90. 90 gets the job done. So I'll put a little 90% up there just to remind me what I'm looking for. Hopefully you're looking at the confidence interval. 90 is the second column. We're looking down here. Can you see the way where the 2 choices are 30, right? Or 40. Can we agree just to go 1.7? Does that seem to be the closest degree, the closest magic t-score to 31? Right, we don't have a 31, but we do have a 30. So I'd be pretty sure that it's going to be closer to the 1.7. So that's all the pieces. And we'll finish off question then. So our 90% confidence interval is X bar plus or minus the magic t-score and the standard error. The average was 70. That was 1.7. And this guy is 717. And we have 1.7 times 0.717. And I get 1.2, oh, let's just call it 22. And so we are looking at 68.78 inches up to 71.22 inches. So if this data was valid, we could be 90% sure that somewhere in that interval is the average height of all college students. If we took everybody who goes to OC and we divided by the total number, the answer we would get would be somewhere in that range. I could phrase this in lots of different ways. Couldn't we say that there's evidence to say that the average height of OC students is less than 6 feet? Would you agree all these numbers are less than 72 inches? So we can say the average height of a person OC is less than 6 feet, right? If I go the other side, couldn't I say it is bigger than 68 inches? The average height is more than 68 inches. So in these kinds of questions, you can talk about there's evidence to prove that it's bigger than this number or less than that number. You don't ask questions like you did in the proportion. Do you know in the proportion ones you could say if the interval was always positive, first guy is bigger than second guy. That's not really happening in this question yet, right? This is just a single value. Do we feel comfortable about the standard process of you get a mean, you're told it, you get a standard deviation, you're told it, you're told how much is in the sample, and then your job is to figure out a 90, 95 or 99, whatever they ask for confidence interval. Do we feel good about that? Right. So what we're now looking forward to doing, I'm looking forward to doing it, hopefully you are, as soon as I find where I put all my pieces of paper. We're now going to move on to the next phase. Oops, there we go. Got my little list. We're now going to look at the difference between two populations, two population means, actually. And there's two flavors of this. This first one is when we have what are called paired differences. And that's the one we're going to start today. And the second one we'll probably see tomorrow, which are independent samples. So it's very similar to, do you know how we did the question, the difference between two proportions, right? P1 take away P2, right? We're kind of doing the same kind of thing, but we're doing it with the difference between the means of two groups, right? We're wanting to compare one group with another. So let's look at what a paired difference is compared to what an independent sample is. If you collect data like they are joined together in some, an example of that might be, and it's the one I'm actually going to be doing as our first example today, is couldn't you take for heterosexual couples the male's age and the female's age, right? The male, right? I forgot what the guy's called. The husband and the wife, right? So male's age, the husband's age, and the wife's age. And we're doing this a heterosexual because if we have other combinations, it's a little bit harder to decide which is which. So that's the only reason I'm doing this. Now, in this case, then you would have a pair of data. You'd have, he got married when he was 21 and she was 23, right? Or you could do it as their age today, right? He's 71 and she's 68, right? But in this kind of situation, the male and the female are connected, right? That's husband and wife. They are a paired difference, right? Another example of paired difference. Can you imagine that you did a math test and then you did a year's worth of math and then you did the SAT again, right? So you did like an SAT and then you had some time off and you did it again. I believe you're not allowed to do the SAT more than once. I think you can, can't you? Right. So let's say you did the SAT in November and then you got your score. And then you did some heavy duty studying and some training and tutoring, and you did it again in January, and your new SAT, hopefully it was bigger, Well, this is you in November. This is you in January. This is somebody else. This is what they got. This is somebody else. That's what they got. Can you see there's like a before and after? They're paired. That's what a paired difference is. So when we talk about what is paired differences about, you take the difference and you call that x1 and you call that x2, right? And you find the difference. And the difference, well, I'll call that x1 and y1 is probably a better way of describing it. And the difference is just x1 take away y1. In other words, you subtract those, and that one would be -2, and this difference would be +3. And so our data may have started off as two numbers, but we convert it into the difference between the two numbers. So the guys we work with are actually just single values. So what essentially that does is it takes two sets of data, right, male, female ages, and it reduces them into a single set of data. And then we do this stuff with it, right? We find its confidence interval. And that's what paired differences look like. The data, the two samples, the two groups, whatever you want to call them, are connected in pairs. Couldn't you have your before weight and then your after weight once you dieted, right? So you got your weight and then you went on a diet and 3 months later you weighed yourself. Wouldn't that be an example of a paired difference data? So what does independent look like? The two samples are totally separate from each other. There isn't any direct connection. So you might ask 100 Americans what their height was, and then you asked 100 Japanese people what their height is. You see, there's no direct link between those two, right? They're independent samples, and that's what we'll deal with tomorrow. So I won't get into any great detail. So, since we are working on difference between two populations, and we're going to be looking at paired differences, let's collect some data. And this is going to be you lot, and I'm going to have to cheat for practical purposes, because really shouldn't my data have, you know, at least 30 numbers, but we'll do it with small data set and just roll the dice and say, yeah, we're probably good, right? So only those who want to share, I'll take it off this screen so I can see us. Oops. Oh, come on. There we go. Your age and your wife's age, or your age and your husband's age, right? So if your husband and the wife, you can do it with your mum and your dad, you can do it with yourself and your partner, you can, and it doesn't need to be religiously married. I mean, if you're living with someone, it's just as good as being married, right? So they count. Your grandparents, you can tell me their age, and I will start collecting data. And I will put in my one. I am 65. And my wife is, oh God, she's going to kill me. Oh shit. Celeste. Oh, she's busy. How old are you? That was a close one. She's 61, she told me. I was going to put 62 down, so I'm glad I didn't. Right, anybody else want to share? I'll do it to this table of still.
My mom's 49 and my dad's 56.
Okay.
I mean, not 56, 46. So my dad's 46, so my mom's 49.
Okay, that works. Next one.
I'm 38. My husband is 40.
Next. Can be your uncle, an aunt, you know, or two friends that you know.
My dad is 49 and my mom's 48.
Right. Got 4 more to go.
My mom,
Right, Wes, go for yours.
oh, my mom is 50 and my dad is 48.
Okay, 3 more to go.
Mom
My
is
mom's-
Well, whoever
sorry.
wants first. Go for it, somebody.
Mom's 52, my dad's 48.
2 more.
My mom is 48. My dad's 56.
And last but not least, whoever's to finish the set.
Dad is 70, mom's 67.
You're lucky you still got your parents, David. Yeah. My mum lived till she was 91. My dad made it till he was 86. Miracle my dad lasted that long. Coal miners do not last as long as my dad did. But he was a stubborn bugger. So you'd have to hit him with an axe to kill him. He was tough as nails. Right, so let's show you how you would do an analysis on this set of data. So we've collected data on male-female partners. We collect a guy here called the difference. Now, just because I've done male to female, that's the way I'm going to do it, right? So that's like X1 and this is like Y1. So 65 take away that is a difference of 4. 46 going that way is a difference of -3. That's a difference of +2. That's a +1. That's a -2. That's a -4. That's a +8. And this one is a +3. So the data that we actually use is the differences. And they use the letter D. So I am going to find the mean and the standard deviation of the differences. Now that will take just a little bit of time, but hopefully not too much. So going to start, going to edit, and here goes 4, -3, 2, 1, -2, -4, 8, and 3, right? So that's the data in. Hit starts, go over to calc, one variable starts, put in L1, and the difference is 1.125 as a positive number. And the standard deviation we are looking for is that guy there, who is basically 4.01. Let's just call it 4. So that's what you would do, or at least you'd get a computer to do it for you. But you would do it with like 5,000 people if you had the money, right? You get really big, good data. Now, what I have noticed right now is that the average difference is a positive number. Now, what that is telling me is that males tend to be, on average, older than females by about 1 year, at least based on this sample, right? Now, can you find females older than males? Darn sure you could. In every world, there's always going to be the opposite, right? But what we're seeing here is a general trend is that the average tends to be, the average difference tends to be +1, which means males are +1 older than females. And about a year difference, right? Not that unreasonable. What we're going to look at now is what, let's do a 90% confidence interval of this data would look like. Well, although it started from a pair of data, do you know that we actually analyze it the same way that we would have done if it had just been a normal single set of data? So the degrees of freedom here, 1, 2, 3, 4, 5, 6, 7, 8, right? The degrees of freedom are 7. Okay, so it's going to be d bar instead of the x bar, plus or minus a magic t squared times s squared over n, right? The standard error. I'm not going to zoom back and forward here. So I'm looking at degrees of freedom 7, and we seem to like confidence intervals of 90%. So can you just trust me that that guy there is in fact 1.89. Can you just say, yeah, okay, I trust you. We know this guy is 1.125. And now we're going to get this fella here. So on my calculator, I'm going to get the square root of this guy, which is 16, divided by n, which was 8. And the answer I get is 1.414. And so what we have now is 1.125, give or take a margin of error. Let's see what that looks like. 1.414 times 1.89. I'm looking at give or take 2.672. Let's check that out. 1.125, take away that number. And we get negative 1.547. And if you add it, you get a 7, you get a 9, you get 7, you get a 3.72. So the average difference between males and female married couples is somewhere between negative 1.5 and it could be as large as what, 3.8. You can ask the same kind of questions that you did with the difference between two proportions. Isn't 0 contained in this interval? That means there is no significant evidence to prove that males are on average older than their female partner, or that females are older than the males. Now, if I'd got an interval that looked like this, would it not mean males are on average older than their female partner by somewhere between 1 and 3 years? On the other hand, I could have got, in which case, wouldn't that represent females are older? Or if you want to phrase it the other way, males are younger, it's the same information, right? Females are older, somewhere between 2 and 3.7 years. So it started life off as a pair, and it became a difference. Paired differences are a very helpful way of looking at before and after situations. Right? So if you wanted to see whether a new treatment had any real effect, positive effect, I'm assuming, couldn't you take a measurement before the treatment happened, and then a measurement after the treatment happened, and then do a difference analysis on it, and hopefully get a nice interval, which was all pluses. So let's do a pretend story like that, right? So they collected data on the before and the after, receiving a treatment to reduce your blood pressure, right? So you had a blood pressure, I'm making numbers up, 110, and then you took it and it became 107. So in that case, your difference would be 3, right? Okay. So what we're going to look at is, imagine that we did a clinical trial with a new drug and we got 150 people in this trial, and it's a before and after deal. So you just measure their blood pressure, right? I think when they do blood pressure, the nursing people will tell me, you don't take the blood pressure of a person and you just take it once. Don't you take the blood pressure of a person, then you take it like a second time. And sometimes you may even take it a third time. Because blood pressure can vary a lot. You know, if you get excited or something, it can go up, you know, for a temporary amount of time. Side issue. You got this guy. We want to see basically, has this reduced? Is there evidence that this drug has actually reduced? Well, and clearly in this case it has, but maybe in the next case it hasn't. Oh, Alexis, you're here. Make sure I can hold off at the end. I need to talk to you as well. So we got 150, we got all the good stuff. Since it's a clinical trial, why do you think clinical trials, when you want to prove that a drug is better or a treatment is better, why do you think they would almost always use 99% confidence intervals rather than the other choices?
You're that much more sure?
Yeah, you just want to be really sure because people's lives or health is at risk. Now, if you're doing questions like, do you like Pepsi or Coke? Isn't a 90% fine? If you screw it up, what's the damage? There's none, right? But if you're talking about some, is this new treatment actually an improvement, right? You want to be pretty sure that when you say yes, it is, there's statistical evidence to say that it is. That you want to be really, really as close as you can be to being sure. There's actually other ones. You know, there's a 99.9% confidence interval. They use 99.9% confidence intervals when you are like as close to being guaranteed as you can be. So NASA will probably be using 99.9% confidence intervals on almost anything that they have to do with their satellites and their rockets. Because those bloody things cost billions, right? You want to make sure that when you measure a bolt, that it's going to fit in that hole, and you know that there's a tolerance of 99.9% sure it's going to fit, right? It's not going to, unscrew on you. So back to the story. In this world, the average differences ended up being 5. So that means that your before was 5 units higher than your after. Well, that's a good sign. Great. That the standard deviation, sometimes they use S little d just to remind you it's the standard deviation, the differences. And let's say that it's 3. Since I'm going to do this confidence interval, it's going to be d bar plus or minus the magic t-score, followed by the standard error of d bar. That's 5 plus or minus, I haven't got that guy yet. This fella is going to be the square root of 9 divided by 150, so I got him. And I'm just going to look at the table over here, and a 99% is on that position, and 150, I'm going to use a 2.63. That's the closest one to 150 I could find. And let's see what we get. It's 5 plus or minus 2.63 times the square root of 9 divided by 150. And that's 0.64. So it's 4.36 and it's 5.64. So we're pretty darn close to being absolutely certain, or 98% certain, that this new old comparison is going to have an improvement, somewhere between 4 and 5 units. In other words, the before will be 4 or 5 units bigger than the after. So this would be a seal of approval for that drug, wouldn't it? That it actually does do what it was intended to do, right? It has reduced the blood pressure. Right? Even although these are positive numbers, isn't before and after, you'd expect that. Now, if I had got wouldn't that be the jury's out? We can't really tell if it's doing any good at all. It might be doing some good, but couldn't it equally be doing some bad? It could be making your pressure worse rather than better. And nobody wants to see this. Because isn't this evidence that you should throw away the formula and never use that drug because this drug actually makes things 6 to 7 units higher. But what we've got now is a nice formal procedure for taking data from a clinical trial, turning that data into differences, and then looking at the before and after differences and giving us an interval of what we think that treatment or drug is now doing. And it takes out all the anecdotal evidence that you could possibly have, right? Because, you know, some people just for no reason get better. As strange as it may seem, I've even heard the stories, although I'm not sure these are true as good diagnosis, but I've heard of people who have just cured, have had cancer and got cured themselves. In other words, the cancer just died on its own. Now, I don't know if that's true, but I've heard anecdotal evidence that that has happened. Right? I so strongly suspect that you were misdiagnosed as having cancer in the first place. And then, you know, when they tested you again, they couldn't find it. And that seems to be more likely. But the human body is a strange creature, isn't it? So maybe you do have a body chemistry that figured out that's a cancer and killed it, because that's basically what your immune system does, right? It looks for things that shouldn't be there and kills them. It's a pretty simple process if it can figure out how to do it. Are we good on differences, or do you want to say another one?
I think I'm good on it. I don't know if everyone else is.
Well, that's what I need to hear. I just need one person to kind of, if you feel shy, just to wave at me or something, and I'll know it's you want one more. Otherwise, I'm going to move on. Okay, looks like it's unanimous. Oh, which is perfect timing because I